first thing we want to start with as far as calculations go is calculating delta G with the standard free energy information from a table. So standard free energies of formation. The values are going to be found in a table in the textbook, but you'll also be given them on the test, either in an abbreviated form, or they'll maybe give you a table on the periodic table and constant sheet. This is our formula. It looks probably really familiar. It's really similar to what we used for calculating delta H if you're given enthalpy of formations, and the same thing that we're going to use basically for calculating the entropy of a reaction, the change in entropy of a reaction. Well, now we're looking at the change of Gibbs free energy in a reaction. We've got to look at the Gibbs free energy of formation of the products and reactants and take the difference. Okay, so the summation of the Gibbs free energy of formation of the products, standard, minus the summation of the standard Gibbs free energy of formation of the reactants. And that's going to give you your change in Gibbs free energy. Remember, if this is a negative factor, it is a thermodynamically favorable process. If this is a positive number, it's going to be a thermodynamically unfavorable process. So let's figure out what it is for this first process. We want to find the delta G for the oxidation of water to produce hydrogen peroxide. So H2O, we have O2, and then 2H2O. Given information can be used. We have the Gibbs free energy of formation of water as negative 237 kilojoules per mole. For oxygen, it's 0 kilojoules per mole. And for hydrogen peroxide, it is negative 114 kilojoules per mole. We do need to think about our, we have to think about our states of matter. We have to think about the coefficients and all that sort of thing. So checking to make sure, I've got H2O2 as a liquid in both cases. This is negative 114 kilojoules per mole. I've got to multiply that by 2 because of the coefficient there. So we're going to do products minus reactants. 2 times negative 114 minus, and then we look at our reactants. I'm going to set up some brackets here. And it's going to be 2 times, for water, it's negative 237, plus for oxygen, I've only got one of them, and it would be 0. So really I don't actually need the brackets in this case because plus 0, we know that's really not going to change anything. So it's just delta G equals, okay, delta G equals 2 times negative 114 minus 2 times negative 237, and just plug that into your calculator to find out what you get. I get a positive 246 kilojoules per mole of reaction. So what that tells me is that this is not a thermodynamically favorable process. It's thermodynamically unfavorable. It can be done, but I need an outside source of energy to push the reaction to force it to occur. All right, we can calculate also, so that was one method using the enthalpy of formations, or not enthalpy, I'm sorry, the Gibbs free energy of formations. We could also calculate using Hess's law. So let's say that I have the Gibbs free energy information of a couple different processes. I've got the process of a diamond being combined with oxygen to make carbon dioxide, or graphite being combined with oxygen to make carbon dioxide. I've got both of those, the Gibbs free energy for that. So I want to know what's the Gibbs free energy for the reaction that is turning a diamond into graphite. So I can combine these reactions in order to make that happen. So as I'm looking at this, I recognize that if I flip this reaction around, then I would end up with the product that I'm looking for. So I want just graphite, and the carbon dioxides could kind of cancel each other out, right? So if I flip this reaction around, the carbon dioxide would become an intermediate, and you could think of the oxygen as being a catalyst, so to speak, if I were to flip this reaction around. And remember, if you flip it around, just like with an enthalpy value, the delta G is going to become the negative of whatever it is right now. So that would become a positive 394 kilojoules. Then we just add these values together. You also need to take into account that if we would need to change the coefficients of the second reaction, I would also have to multiply by whatever number that is. I would multiply the same number times the delta G value. In this case, I don't need to multiply by anything except a -1. I just need to flip this around to get a -1. So if I were to calculate this, I'm just going to add those two values together. But remember, since I flipped the second reaction around, I've got to make it a positive number. So it's going to be negative 397 plus 394, which of course is -3 kilojoules. All right. We could also calculate it using standard cell potential. We'll get into this more when we talk about electrochemistry in a few days. Delta G standard equals negative NFE, where N is the number of moles, F is Faraday's constant, and then E standard is the cell potential. Then we have delta G standard being calculated using the equilibrium constant. That can be calculated by doing negative R, the gas law constant in the correct units, R times T times ln of K. That ln was doubled there, it shouldn't be. I'll try to fix that. So it's delta G equals negative RT ln K. Talking about the equilibrium constant there. It could also be calculated using delta H and delta S values, and I do want to talk to you a little bit about this today. So delta G equals delta H minus T delta S. We've talked about delta S, and now we've talked about what delta G is. Think about the signs here. We'll spend a little bit more time doing this later, but I want you to think about what is favorable, what makes delta G negative. Well, having a negative delta H helps to make delta G negative. So that's an exothermic process. If you have something that's exothermic, it helps to make delta G negative. And what would help to make this factor negative? Well, since it's already got a minus sign here, it would be to have delta S be a positive number. So the most favorable thing to make delta G negative is for delta H to be negative and delta S to be positive. That's what makes the most ideal process for thermodynamic favorability: negative delta H, positive delta S. A process like that is thermodynamically favorable no matter what the temperature is. But then we'll talk about how if you get a mix of it, let's say I have a positive delta H and a positive delta S, well then we could think about what would happen at higher temperatures or at lower temperatures. Or if I had a negative delta S and a negative delta H, we could talk about how temperature would affect that. But there's a type of process that is never thermodynamically favorable, and that is if both of these factors are going to be positive. So if I have a positive delta H and a negative delta S, remember negative times negative is positive, so I have positive and positive factor, delta G would always be positive no matter what the temperature was. So positive and negative, positive delta H, negative delta S, that is never thermodynamically favorable. If I have a negative delta H and a positive delta S, that is always thermodynamically favorable. And we'll go into that in a lot more detail later on. We'll have another reminder about that. Note that T is always going to be in Kelvin for this formula, for really any of the formulas that we have here in the thermodynamic section. T is always in Kelvin. Delta G and delta H are usually in units of kilojoules per mole, where delta S is usually in joules per mole Kelvin. So be careful. Make sure that your kilojoules and joules are consistent before you proceed with your calculations. You're going to have to convert one of them often in order to get the correct calculations, especially if you're using this formula where you have delta S, delta H, and delta G all in the same equation.